Hello all of you. Welcome to the 18th lecture in the course on analysis and modeling in chemical engineering. In the previous lectures, we discussed how to perform mole balance on chemical reactors, and we discussed the examples of different kinds of reactors like batch reactor, CSTR and PFR. So today I am going to put that into practice by doing some examples that demonstrates how modeling is used in chemical reactor engineering. So we'll begin with a simple example on a batch reactor, and the problem statement goes like this. In one of the practical class of certain hours, let's say tau hours, students are asked to prepare red dye in a batch reactor using the reaction A to B, where A is a colorless reactant that give rise to a product B, that is red, which is a liquid phase reaction and following first order kinetics. Now, the final objective in this case is to obtain a sufficiently red solution, and that will happen when the concentration of B, that is the colorless, the red product, is higher than threshold value. It can be any threshold value. The experiment starts with a feed solution of certain initial volume V in the batch reactor and certain concentration Ca naught of A. And after almost halfway, tau by 2 hours, tau is the full experiment, tau by 2 hours from the beginning, seeing that the solution is not sufficiently red, there is an impatient student who adds another volume V of the same feed solution, that is having the same concentration Ca naught of A. And then the question is, will the student be able to finish early? That means, will he reach the threshold value earlier than the case if he had not added that, right? So, let us take two situations. One is a patient student who continues doing the same thing for tau hours, and then there is an impatient student who adds this feed solution, another volume V of feed solution at after half the time. So, we need to compare the concentrations of B that we obtain at time tau after the beginning of experiment for both these cases, impatient and patient, right. So, if for example, the impatient student finishes early, that means he reaches the threshold value earlier, then the concentration of B we will obtain at time tau for the impatient student will be lower than, actually higher than the concentration of B that we obtain for the patient student, right. So, let us look at this example, and we will begin with the reaction A to B, and it is said that it is a first order reaction. So, we have the rate law minus R A is equal to K C A, and let us now perform simple mole balance for this case. It is a batch reactor, and it is also a constant volume batch reactor because we are considering a liquid phase reaction. So, we can assume that there is no volume change that is happening in the system, right. So, liquid phase. So, we can assume that the volume remains constant, and therefore, the mole balance is going to be something like this: dCA by dt is equal to minus Kca, that is equal to Ra essentially, and this gives me, since the concentration of A at time 0 is Ca naught, we can integrate this and we will get something like Ca is equal to Ca naught exponential of minus K tau. This becomes the concentration for the patient student at time tau. So, let me note down here, this is for patient student. It reads weird, but it is like someone who is not impatient, right. Okay. Now, let us find the concentration of B also after time tau. So, after tau, assuming that we began with no B in the beginning, what we are going to have is the concentration of B is equal to the concentration of A that is consumed, which is Ca naught minus Ca, and that gives me Ca naught into 1 minus exponential of minus K. Now, let us keep this with us, and we are going to compare this for what we obtain for the impatient student, right. Now, if we have impatient student, then until time tau by 2, basically it is same as the case of a patient student, right. So, at time t is equal to tau by 2, the concentration of A and B can be obtained by simply putting time equal to tau by 2 in these two equations. So, we will have C A is equal to C A naught exponential of minus k, and now the time is tau by 2, and C B is equal to C A naught 1 minus exponential of minus k tau by 2. Okay. And now at this particular time, he is basically adding another volume V of the feed solution, right. So, this is before the addition of another volume of feed solution, right. And let us see what is going to happen after the addition. So, after addition of volume V of the feed solution, what we need to keep in mind, where often people do mistake, is to note that both the concentration of A and B are going to change, because in the feed solution there is no B, and the concentration of A in the feed solution is again Ca naught, right. So, let me now call these concentrations as Ca1 and Cb1, just to ensure that this is the concentration before the addition of the feed solution, right. And after addition, we will have another concentration, and we can do it by the mole balance. So, for A, we are going to have the concentration after addition, let me call this Ca2, into the volume, which is now 2V, becomes the number of moles of A after the addition of feed volume, right. And that is equal to whatever number of moles we have in the reactor, which is Ca1 into V, and whatever number of moles we have added in the feed solution, which is Ca naught into V, right. So, therefore, my Ca2, which is the concentration of A after the addition of this feed solution, is going to be something like Ca1 plus Ca naught by 2, and we already have obtained the expression of Ca1 right here. So, if I plug that in, we are going to have something like Ca naught by 2 1 plus exponential of minus k tau by 2. Now, do the same thing for B. So, let us say the concentration of B after the addition of feed solution is Cb2, and the total volume now is 2B, that is equal to the concentration of B before addition, that is Cb1 into V, and now the feed solution does not contain any B. So, we will have 0 concentration or 0 number of moles in the feed solution. So, therefore, my Cb2 is going to be Cb1 by 2, which is essentially using the expression of Cb1 we have obtained earlier, is going to be Ca naught by 2 1 minus exponential of minus k tau by. And now, the reaction will proceed from this concentration until the end of the reaction, that is at time tau. So, we will start from this value now, right. So, let me now find the concentration at time tau. So, at time tau, for the impatient student, the concentration is going to be Ca is going to be whatever Ca2 we have obtained, that is the concentration of A after the addition of the feed solution, into exponential of minus k tau by 2, because we still have first order kinetics, right. And plugging in the value of Ca2 that we have obtained, what we will get is something like Ca is equal to Ca naught by 2 1 plus exponential of minus k tau by 2, and then we need to multiply this with exponential of minus k tau by 2, right. So, this is the concentration of A at the end of time tau for the impatient student, right. And now, we are also interested in finding the concentration of B. That will be the concentration of B now that we have started with, and the concentration of B that is coming from the reaction between the times tau by 2 to tau, right. So, the new conversion that has happened in the time window of tau by 2 to tau, that we have to basically account for, right. So, this is going to be Cb, basically Cb2 here, that is the concentration of B after addition of feed solution, and this plus whatever Ca2 that we had at time tau by 2 minus the Ca, that is the amount of A that is converted in time tau by 2 to tau. So, this is what we have to essentially add up in order to get the concentration of B at time tau, right. So, let us do that. So, this is going to be Cb2 will be equal to whatever we have obtained earlier, Ca naught by 2 1 minus exponential of minus k tau by 2, and then Ca2 minus Ca will be, so Ca2 basically is until here. So, Ca2 minus Ca will be something like Ca2 1 minus exponential of minus k tau by 2, and now I can substitute for Ca2 here from this expression, and that gives me Ca naught by 2 1 minus exponential of minus k tau by 2 plus Ca naught by 2 1 plus exponential of minus kappa tau by 2 into 1 minus exponential of minus k tau by 2, by the way both are k. So, this will now give me something like Ca naught by 2 1 minus exponential of minus k tau by 2 can be taken common into 1 plus this quantity, which is 2 plus exponential of minus k tau by 2, right, and this will give me something like Ca naught into 1 minus exponential of minus k tau by 2, and I will put the 2 from here and divide in the second term, that gives me 1 plus 1 by 2 exponential of minus k tau by 2. So, now I can compare this with the case of patient student by kind of factorizing whatever we have obtained here for the case of B. So, I will try to factorize this expression in equation 2 here, and I can do that by basically using the relation 1 minus x square is equal to 1 minus x into 1 plus x, and in this case x is equal to exponential of minus k tau by 2. If I square it, I will get exponential of minus k tau right here. So, this becomes Ca naught into 1 minus exponential of minus k tau by 2 into 1 plus exponential of minus k tau by 2. Now, let us compare whatever expression that we have got here, let me call this equation 3, with whatever expression we are getting now for the impatient student, and what you see is until the first term both the expressions are the same, but in the second term we have 1 plus half of exponential of minus k tau by 2 for the impatient student, and in this case we have 1 plus exponential of minus k tau by 2 without an half here. So, clearly the concentration that we get here by equation 3 is more than the concentration we get there in the impatient student case. So, therefore, impatient student will have lower concentration of B at time tau, and therefore, impatient student will not be able to finish early, because the concentration of B he is getting is smaller than compared to the case of a patient student, right. So, the key idea is to note that we have done in 2 steps until tau by 2 and then from tau by 2 to tau, and whenever we add the feed solution, we need to look at the concentration of both A and B, and if we do the mole balance properly, only in that case we can get the correct equation, right. So, it is very important to use the mole balance very carefully at every step of the process, in this case before addition, after addition, and after addition to the end of time for the impatient student. So now I will take another example, and in this case we are looking at CSTR, but this is an unsteady operation of a CSTR. So we have some reaction A going to products. It's an elementary reaction, that means the rate is minus RA is equal to KCA. The products are not relevant in this problem, that is why I am simply saying products. It is a liquid phase reaction. So again we can assume that the volumetric flow rate is not changing in the reactor between the inlet and outlet, and we can assume that the conditions are also same in this case, right. And we are asked to derive the expression for the transient or unsteady state behavior of the CSTR, and we ask when will steady state be achieved, and there are two time scales in the problem. We have to identify those two time scales and to discuss their significance, right. So let us begin with what we are doing for a CSTR. So we had a CSTR, we begin with certain concentration of A. Let us assume that there is no product to begin with. So we have pure A with a concentration Ca naught and with some volumetric flow rate V, that is same as the volumetric flow rate in the outlet, but the concentration is now Ca. And now we can also define a conversion. Ca is equal to Ca naught into 1 minus x, where x is the conversion. The only thing is this, the Ca here is a function of time. We are doing unsteady state, and therefore x is also a function of time. Now, if you look at this problem from the very initial, let us say I am assuming that a CSTR is being filled with the liquid first, and then the reaction starts, and then eventually we have a steady state. Now this becomes somewhat complicated, because in that case the volume of the CSTR will also become a function of time, right. And at least in the very beginning, you should have a situation where there is no outlet and there is only inlet. So it must be running in some kind of different kind of an operation, where the volumetric flow rate is only there in the inlet, not in the outlet, in order to fill the tank, right. But after that, once we eventually reach a certain volume V, we may want to maintain that volume, and now we want to wait until the concentration becomes constant, right. So we are going to therefore assume that the tank is already filled and my V is now constant. Only then we can assume that the inlet volumetric flow rate is equal to the outlet volumetric flow rate. Otherwise, you will have an initial period where one of them, the outlet, has to be 0. If I assume V to be constant, then also the concentration of A in the tank will change with time. We can still assume that the concentration of A in the tank is same as the concentration of A in the outlet, because we have perfect mixing, but it will take some time to reach steady state. So let us try to write the general mole balance for this problem, keeping in mind that now there is no steady state. So we have to consider the accumulation term here. So general mole balance will give you the molar flow rate of A that is coming in minus molar flow rate of A that is going out, plus the rate of generation of A. In this case, the A is getting consumed, so RA is going to be negative, and this will be equal to the accumulation d and A by dt, right. So since my volume is constant, I can write this as V into dCA by dt, and RA we already have identified is the first order reaction. So RA is equal to minus KCA, and molar flow rate is simply Ca naught into V, and in the outlet again Ca into V. So therefore we have the expression V into Ca naught minus Ca minus Kca V is equal to V dCA by dt. Let me write this expression in terms of the conversion. So then we have Ca is equal to Ca naught into 1 minus x. So the first term will give me V Ca naught x minus K Ca naught 1 minus x into V is equal to V Ca naught dx by dt, but now with a negative sign, because Ca is equal to Ca naught into 1 minus x. Right? Now we can divide this expression by V, and once we do that, we will have a term containing a small v by capital V. So let me call that quantity as a one time scale, and then we also should note that this k is also something like inverse of time. The unit of k is the inverse of time. So therefore, we have another time scale coming from there, right. So let us look at these two time scales. So we have the expression we just now got, v Ca naught x minus k Ca naught into 1 minus x into v is equal to minus v Ca naught dx by dt. That is what we had there. And now I am going to divide this expression by v, and then Ca naught automatically cancels out, and then we have something like x divided by v by v. There is a reason why we write like this, and I will come to that, minus 1 minus x divided by 1 by k, and this is equal to minus dx by dt. Right. What you note here, the way we have written it, this denominator, the volumetric flow rate, has a unit of time, and therefore we call it a name tau h, and I will call it a hydraulic time scale. The reason being that this is something which is completely in our control. It is pure hydraulics. We can control the volumetric flow rate, and therefore we can control this time scale for a given volume by changing the volumetric flow rate, by changing the pumping or whatever. We can change the volumetric flow rate, and we have a control on this time scale, right. On the other hand, this quantity is also having a unit of time, but this is not really in our control. This is the time scale that is given by the reaction. Whatever chemical reaction, it will have a certain rate constant. Of course, I can work with a higher temperature. That way, I can control the rate constant, but nothing like the volumetric flow rate, which is much easier to control, right. So this one is defined by the reaction, and the only way to possibly control that is by using a high temperature or by a catalyst, but this one is something which is easy to control, right. Let me call this quantity my tau r. So now by some rearrangement, we can get something like this, dx by dt plus x, and then we see we will have a term 1 over tau r plus 1 over tau h on the left hand side, and this will be equal to 1 over tau r on the right hand side. So basically, we have moved dx by dt on this side, and we collect the terms containing x on the left hand side. So now we can notice that this is a linear differential equation of first order. So we will have an integrating factor, and that is exponential of 1 by tau r plus 1 by tau h into t. And if I plug that in there, what I will get is something like d by dt of x into my integrating factor, that is exponential of 1 by tau r plus 1 by tau h into t, and this also gets multiplied on the right hand side. So we have 1 over tau r exponential of 1 by tau r plus 1 by tau h into t, and now we can integrate this. So on the left hand side, we have this integration. The upper limit gives me this quantity, and the lower limit will correspond to a conversion of 0. So basically, we will stop here. The lower limit will be 0, and that will be 1 by tau r, and the integration of this quantity, which will give me exponential of 1 by tau r plus 1 by tau h t divided by 1 by tau r plus 1 by h, and this has to be between the limits 0 to t, and that gives me 1 by tau r exponential of 1 by tau r plus 1 by tau h t minus 1 divided by 1 by tau r plus 1 by tau h, right. Now we can divide it by this term, and then we will get a nice expression. It will be x is equal to 1 by tau r divided by 1 by tau r plus 1 by tau h into 1 minus exponential of, now we have a minus sign, 1 by tau r plus 1 by tau h into t. So, this becomes the expression of the conversion x. And now you can ask, when we will have a steady state? We will have a steady state when the second term here that contains the dependency on time, it goes to 0. That will of course happen for time infinity, but in this case we can assume that once this time is much bigger than this time scale that is given by the harmonic mean of tau r and tau h, in that case we can assume that a steady state will happen, right. So, we can rewrite the second term as something like exponential of minus t by the harmonic mean of tau r and tau h, and whenever this t is much bigger than this harmonic mean, we are going to have a steady state, right. So, clearly steady state is only an approximation. We do not have a true steady state, but once this condition is met, we have close to a steady state. And as you know, the harmonic mean is closer to the lower value. So, whichever is the lower value among tau r and tau h will pretty much dictate when the steady state is going to be true. Let us say, for example, your tau r is 1 minute and your tau h is 1 hour, right. So, whichever is the smaller value here, that is going to basically dictate when do you have the steady state conditions. So, it is going to be something like a harmonic mean of tau r and tau h, if you want to think it that way. But essentially what this means is whichever is a bigger time scale, that is whichever is a slower process, is going to dictate the time scale that will be used here, right. So, for example, if you are having a fast reaction, that would result in a smaller value of tau r, and if you have very less volumetric flow rate, in that case you will have a much larger value of this tau h, right. So, together both of them will dictate the behavior. So, whichever is the slower process essentially will tend to dictate the behavior, but once we reach steady state, then the conversion is given by only this, because the time dependence is going to go away in that case, right. So, with that I want to conclude the discussion today. In the next lecture, we will do couple of more examples on the reactor design problems, and then we will go to the energy balance problem of the chemical reactors. So, with that I stop here. Thank you so much.